This week's main topic is about partial derivatives, which is the multi-variable version of the differentiation that we learned last semester. So let's make a note right here that partial derivatives are for multi-variable functions. For multi-variable functions. Alright? Before we get into the details of this new topic, let's talk about something that we learned in Cal 1. So in Cal 1, we work with single variable function. So it's going to be on right here. Let's make a note right here. Let's spend some time on this single variable functions of fx. And as you know, this function has only one input, which is x. We can put any values of x in as long as x is in the domain set. And in the end, we sometimes assign this function value to a new variable called y. So we have this in Cal 1, and then we perform this operation called differentiation, and we turn this function into a different value. Right? We diff this, and of course, when it comes to differentiation, we have to differentiate with respect to a variable. So here we are going to differentiate this with respect to x. Always diff with respect to an input variable, and in this case this is x. Alright, WRT here stands for with respect to, and in the end we get this df by dx. Right, let's make a note right here. We have this d of fx by dx, which means that we have done the differentiation on this function with respect to x. And sometimes we see this form as well, f prime of x, same meaning. And since we assign in here, we assign this function value to this y, this new variable. So sometimes you see this notation as well, dy by dx. All right. So sometimes we see this dy by dx because this y is equal to f. And sometimes you see this y prime. Alright, all these four have the same meaning, which is the first derivative of this function with respect to x. So let's make a note right here. What you see right here is the first derivative of f with respect to x. Alright. Okay, in terms of meaning, let's take a look at number one. Geometrically, when you talk about this first derivative, you think of the slope of the tangent line. So let's make a note right here. You find the first derivative, it's going to correspond to the slope of tangent line, tangent to the curve of fx. Alright, tangent line. Okay, now that is in terms of geometry. And you can also view the first derivative as other physical meaning as the rate of change. Right, number two, as a rate of change of this function, rate of change of fx with respect to x. Right. Okay, now that is something from the last semester, and let's put a break on this one first. The reason that I need to bring this up here is that I want to connect this to what we are going to learn today. And it's going to me, it's going to make things a little bit easier to understand. Now back to this new topic of today, which is the partial derivative. We are going to apply it on multi-variable functions. And here today it's going to be about multi-variable functions. It's going to be quite similar to what we just did. In terms of multi, alright, we are going to have f of x and y instead. You can have z as well, but let's stick with just two for now. So here we have two input variables, x and y, and just like before, we are going to assign this f function value to a new variable, and that is z. Okay, notice that z is different from x and y. Z takes the value of the function. So, alright, now we are going to do the same thing. We are going to diff this function, perform the same similar procedure that we did last semester. But then, in this case, we have two variables to consider. One is x and one is y, and the other one is y, which is different from in Cal 1. We only have one. We don't need to make a choice. But now we have two, so we have to choose one. And I'm going to choose x first with respect to x. Alright, so here I'm going to get this first derivative of this function, and here for partial derivative we are going to use this curvy d. Right before it's just regular d, here I'm going to use this curvy d, df of xy with respect to x. Alright, and sometimes we use this notation just f, and with the subscript here of x, same meaning, so the first derivative of f with respect to x. But as you can see here, we have another variable to consider, which is y, another input variable. So we can perform the same procedure with this y. So let's make a note right here. This one is differentiate with respect to y. And I'm going to get something similar. df with the curvy d, df of xy with respect to y. And we can also use this f with the subscript of y. Okay, now we have more forms of this first partial derivative of f, and which is going to be related to this z. Alright, so sometimes you are going to see this form as well. dz by dx, alright, or z with the subscript x, right? Same with y, dz with respect to y, or z with subscript y. Alright, so what you see right here, all of these forms have the same meaning. They are the first partial derivative of f with respect to x and y. So let's make a note right here that all that we have right here are the first derivative, first order partial derivative of f of x and y. The first row is with respect to x, the second row is with respect to y. Alright, so we have two sets of partial derivatives here, but if you have one more input value like w, then you are going to have another row of this partial derivatives. Now in terms of meaning, let's take a look here. So let's take a look at this dz by dx, the first partial derivative with respect to x, or you can use this f with the subscript x. It's going to be quite the same as what we had before. It's going to be similar to the slope of the tangent line in the single variable function, but here we have two dimensions, so it's going to be a little bit different. So let's add a note right here. It's going to be quite the same, quite similar. It's going to be the slope of tangent line, again tangent line to the surface of fxy. Oh, by the way, this time this function is no longer a line or a curve, it's a surface. Alright, so we are talking about a tangent line to a surface, and the surface that we are looking at in this figure is this blue surface. This blue surface is the z equal to f of x and y. Alright, now this is not done yet. Slope in the slope of tangent line of this surface fxy in the direction of x. So this is important. In the direction of x. So we are looking at the change in this direction only with respect to x. So here in the direction of x means that this is with respect to x. So let's take a look in this figure. The direction of x is going to be along this x-axis, right? X. which means that the tangent line is going to be parallel to the x-axis. So this is going to be what you see right here. This is the tangent line in the direction of x variable. All right. So let's make a note right here. This is tangent in x direction, and that's going to be this. The slope of that is going to be the dz by dx slope, and with slope equal to dz by dx. All right. Now, as you can see here, we have another dimension to consider. So we are going to take a look at dz by dy, all right, which is this one. And the meaning of this one is going to be similar to the one that we just did. It's going to be the slope of the tangent line to the surface of f in the direction of y. Make a note right here. What you see right here is the slope of tangent line, all right, to the surface of fxy in the direction of y. And in the direction of y right here. And the reason for that is because we differentiate this function with respect to y right here and y right here. So the direction of y, we are looking at this direction, right, along the y-axis. So the tangent line to this surface is going to be this line, this red line, this new one, which is parallel to the y-axis. And what you see right here is the tangent line in y direction. Tangent line, so let me save some space here. Tangent line in y direction. Tangent in y direction. And the slope of this, slope equal to dz by dy. Alright, so we have two tangents lined here. One with respect to x and the other is with respect to y. And if you use these two tangent lines to create a tangent plane, it's going to be this one. With these two, we can create this tangent plane. Alright. So when we talk about the tangent of a surface, it has to be tangent plane. Alright. Okay. So tangent plane right here at point P is created by these two tangent lines. Created by two tangent lines. Alright. These are the concepts, but now let's move to the calculation. I am going to give you just one tip for the calculation, and after that it's all practice. So just one tip to follow right here. One tip: when performing partial diff on a variable, if you work on a certain variable, then you treat other variables as constant. On a variable, you need to treat other variables as constants. That's all you need to remember when it comes to partial derivatives. If you work on x, alright, this is the key right here. If you work on this dz by dx, you just treat y as constant. For this one, treat y as constant. But if you work with dz by dy, you are going to treat x as constant. Okay? So now that you know everything you need to know about these partial derivatives when regarding the concept and how to calculate, let's try these on the examples in the next slides. So let's take a look at this number one here, the easiest one. So here we have a multivariable function f with two inputs, x and y. And this function is equal to all these terms. 2x squared y cubed minus 3x squared y, and so on. We have quite a lot of terms here, but in the end we are supposed to find the first order partial derivative of this function with respect to x and also with respect to y. So what we need to find here is df of xy with respect to x and also df of xy with respect to y. Let's start with the first one, which is df by dx. So we can use this notation as well, the subscription of the x variable. This tells us that we are working with x right here, and we are going to perform the differentiation only with x variable. Here we are going to use the tip that I mentioned earlier about treating other variables to be a constant. Here we work with x, which means that we are going to treat y as a constant. So please make a note right here. In this case, for fx, we are going to treat y as a constant. Alright? Which means that y is not going to change. All we need to do right here is to study the value of x. Okay? So let's find out about this fx. So this is going to be equal to d of f xy dx. And as you know, we are working with x variable, so I am going to focus with just x in this function, which is right here, right here, right here, and the rest besides this are going to be constants. So let's start with the first one. I am going to differentiate all of these terms. The first term, we have this 2 is going to stay the same because it's a constant and it's multiplied in. Here I have to differentiate x squared. I get 2x. Y cubed. Here y is a constant. I told you earlier. Y as a constant, and this is multiplied in, so I leave it be. Y cubed stays the same. Next, 3 stays the same. I diff x squared. I get 2x. Y right here multiplied in. I leave it the way it was. So y stays the same. Next, we have 2, and I need to diff this x squared. I get 2x. And for the next term, as you can see here in this term, there is no x, which means that the whole term is basically a constant. Y doesn't change here. So if I diff this constant with respect to x, it's going to be equal to 0. Okay? It's going to be equal to 0. It's a little bit strange because we have this y, and looking at this is a variable. But keep in mind that in this case, we only focus on the x variable. Y doesn't change, so maybe write it down here that y doesn't change. Y does not change. Alright, so if we diff that, it becomes 0. Now the last term is just 1, and we diff this with respect to x. Of course, this is a constant. We get 0 at the end. So let's work out all these terms in terms of calculation. So we have this 4xy cubed minus 6xy, alright, plus 4x. And there you go. What you have right here is the first order partial derivative of f with respect to x. So make a note right here. This is first order partial derivative of fxy with respect to x only. Okay. Now that we have fx, let's find fy. Partial diff of f with respect to y. And here we are working with y variable, which means that we are going to treat x as a constant. X is not going to change here. So right above here, that treat x as a constant. In this case, x is not going to change its value. We are studying on the y-axis. So make a note right here that x doesn't change. Alright, so what we need to find here is df, same thing, of x and y with respect to y. Okay, so here we work with y, so we are going to focus on the y variables in the expression of the function. So y is right here, y right here, and y right here. So let's diff the first term with respect to y. The rest I treat it as a constant. So 2x squared is constant, it stays the same. Now I need to diff y cubed, I get 3y squared. Alright, next term, 3x squared stays the same because they are constant in this case. And I diff y, I get 1. Alright, next term, I have this 2x squared. Here we work with y, so 2x squared is considered to be a constant. You diff a constant with respect to y, then you get 0 out of that. Now next term we have this 3y squared. So 3 stays the same. And I diff y squared, I get 2y. And last term I have this 1. I diff that with respect to y. A constant becomes 0 here. Now let's work out all these terms. We have 6x squared y squared minus 3x squared plus 6y. Alright, and that is the answer for fy, which is the first order partial derivative of fxy with respect to y. In other words, this is the slope of the tangent line in y direction, and fx is the slope of the tangent line in x directions. Alright, so as simple as that. Alright, just one tip with the treat other variables as the constant right there. Okay, so let's try example number 2 right here. In this example, we are supposed to find the second order partial derivative, okay, of f, and this is coming from example number 1. Okay, so we have to use the information that we got from example number 1, so I'm going to write it down here again. So let's write down the first order right here, first order partial derivative. We have this fx, and that is equal to, so I'm looking at this one, alright, 4xy cubed minus 6xy plus 4x, right? And we have two of them. The other one is the partial diff of with respect to y, that's equal to this expression, and that's equal to 6x squared y squared minus 3x squared plus 6y. Okay, let's move to number 2 right here. Now we have the first order derivative written down. Our job is to find the second order derivative. Alright, the question is, what are they? What do they look like? So let's take a look here. So we start with this f, right, of xy, and then we diff this. We diff this to get the first order derivative. So we get this fx, okay, and we diff this with respect to y to get fy. Alright, so let's make a note here that here we diff with respect to x and diff with respect to y. And what you have right here is the first order partial derivative. Now we have to move further, which means that we are going to diff again. For this fx, I can diff this again with respect to x to get this second order partial derivative. And it's going to be called x and then x again. Okay, so make a head note right here. This is second order partial derivative. But as you know, when it comes to differentiation of this multivariable functions, we have two choices to make. We have x and y. I just did x, so which means that I can do y as well. So this second order partial derivative is going to be fx and then y, right? Same with this fy, I can diff this fy with respect to x. So it's going to be f with respect to y first and then x later. Okay, same thing here with respect to y. It's going to be f with respect to y first and then y again. Check out this order. This first x is the first derivative and this second x is the second derivative, right? 1 and 2, 1 and 2. So don't mix it up. They mean different thing. xy or yx. Okay. This xy right here, it means that you diff with respect to x first and then y later. But for this one, you diff with y first and then x later. Okay. Now, it means that at this point, we know that the second order partial derivatives, we have 4 of them. All right, we have 4. But when it comes to the first one, we have only 2. The first order partial derivative. And then if you move to the third, it's going to be what? Well, double of that, right? 8 for third order. All right. But we are not going to go there right now. Okay, so this 1 and 2. Okay, so our job here is to find them all. So we have to find fxx, fxy, fyx, fyy. Right here we are going to find fxx, fxy, fyx, and fyy. Alright, quite a lot of things to do. So let's start with the first one. So here the first one is partial diff with respect to x and then x again. Alright, you can express this as you have this fx right here and you perform the differentiation with respect to x. Okay, and you can express this as the second order derivative of f with respect to x twice. Okay, now this is going to be equal to something, and let's do the calculation. Here we are going to diff this fx with respect to x. So we are going to focus on this expression of fx here, and we are going to diff it with respect to x. So taking a look here, I am interested in the x variable. So x is right here, and right here. So let me diff this. Diff the first term, we have this 4, x becomes 1, and y cubed stays the same, because for this one, we treat y as a constant. So make a note right here that treat y as a constant, Alright, so here let's move to the next term. 6 stays the same, x becomes 1, and y stays the same. Plus 4x, differentiate 4x with respect to x, we get 4. So in the end, we have this 4y cubed, alright, minus 6y plus 4. Alright, and this is the second order partial derivative, the first one, with respect to x and x. Okay, now let's move to the next one, which is the f of x and y. Here we are going to partial diff of x with respect to y. Alright, so this can be expressed as the second order partial diff of f with respect to x first and then y. Pay attention to this. The order of this, we perform this x first and then y later. So as you can see here, the order here is a little bit different from what we have above right here. So pay attention to the meaning of this. Okay, so back to here, we are going to diff with respect to y, which means that we are going to treat x as constant. Alright, so back to this fx again. I'm going to look at this again, and I'm going to diff this with respect to y. And y is right here, y is right here, and we can diff the first term, and we get this 4x stays the same. Y cubed, I get 3y squared. Alright, next term, 6x stays the same, y becomes just 1 if I diff that. Plus 4x, this time around, this 4x is considered to be a constant because we are working with y right now. So diff a constant with respect to y, I get 0 plus 0. Okay, so I have this 12xy squared. Alright, minus 6x, and that is the second order partial derivatives, the second one. And this time with x with respect to x first and then y. Okay, the order is like this, x first and then y. Now let's take a look at the next one, the third one, f of y and x. Okay, so here we start with this fy and we are going to diff this with respect to x. Okay, now the order is this: we start with y first and then x next. Okay, and we can express this as the second order partial diff of f with respect to y first and then with respect to x. As you can see here, this is y first and then 2 right here. So let's work on this. We are going to diff fy with respect to x, which means that we are going to treat y as a constant here. Y as constant. Alright, so we are going to diff y, so I'm going to switch to this one and perform differentiation on this one with respect to x. And I look at this and I see x right here, x right here. So let's diff that. The first term I diff that with respect to x, I get 6, stays the same, x becomes 2x, right? And y squared stays the same. Minus 3 x squared, I diff that with respect to x, I am going to get 2x out of that. With this 6y, if I diff that with respect to x, there is no x there, so this is a constant. So I am going to get this 0. Okay, now work out these terms. I get 12xy squared minus 6x. Alright, and that is the third second order partial derivatives. I want you to look at something here. Take a look at fxy, the second one. This is equal to 12xy squared minus 6x. And the third one, fy of fy and x, we have this 12xy squared minus 6x. You can see that fxy and fyx is equal, and the equality that we have here is not a coincidence. Alright, so make a note right here that fxy equal to fyx. Alright, which means that when it comes to partial derivative, the order of this operation doesn't really matter. Okay, make a note right here that the order of operation does not matter. You can perform differentiation with respect to x first and then y later, or y first and then x later. They are going to come out to be equal. So the order doesn't matter here. Doesn't matter as long as, this is important, as long as the number, okay, I'm sorry about this space, the number of times are equal. For example, this one, we diff with respect to x once and y once, and same here. X once and y once on the left hand side, and this y once and x once on the right hand side. As long as the number is equal, then you have the same result, even though the order can be switched around. Okay, the last one, the last second order partial diff, f of y and y. So here we are going to start with just fy. Alright, and then we are going to differentiate this with respect to y. And as you know, we are working with y variable here, so we are going to treat x as a constant. Okay, so here can be expressed as the second order of f with respect to y twice. So there you go. Now we are going to take a look at this fy and diff that with respect to y. And y is right here and y is right here. Now this is, the first term is equal to 6x squared, which I don't touch, and y squared becomes 2y minus 3x squared. This one doesn't have y, And here we treat x as a constant, so this whole term is a constant here. So when you diff a constant with respect to y, you get 0. Now the last one, plus 6y, we diff that with respect to y, we get plus 6. So here the last second order partial diff, we get 12x squared y plus 6 as the final answer.